Lorenzo Leone on magic-induced computational separation in entanglement theory.
Is it working? Oh, perfect. Okay. So thank you for coming, everyone. So again, I'm Lorenzo Leone, a postdoc in the amazing group of Jens Eisert in Berlin. And today I will talk about this topic. You can see here 3 keywords already: entanglement, magic, and computational efficiency. And I hope by the end of the talk, it will be clear how I will merge these concepts together. So let me first acknowledge my wonderful co-authors. Without them, nothing on this would have been possible. So Andi, which is also here at QIP, is a PhD student in Harvard University, and Salvatore Oliviero is a postdoc in the Vittorio Giovannetti group in Pisa. Okay, let's start. So this is the punchline of my presentation. I will first give you some motivation and basic setup. Then I will describe the results. And finally, I will try to convince you in this small section here, methods, what are the ideas behind the results. And then I will quickly summarize. OK, so most of you should be familiar with the concept of entanglement. And the good news is that here we are dealing with the simplest entanglement theory setup. Bipartite pure state entanglement theory. It is well established. It's maybe the simplest. Here you have Alice and Bob, which are very far apart to each other, and they share a big entangled state. Here we need to imagine that we have always many qubits. So in this theory, you can quantify entanglement very well by the mean of this spectral function here that you all know is the von Neumann entropy. And here I'm displaying the most important entangled state, which is the APR pair or Bell state or E-bits. On the other hand, here we have magic. I think that the takeaway message for magic is that it is a basis-dependent quantity. We like the operator basis of Pauli operators. And to any state psi, you can associate a subset of those Pauli operators, the ones that act identically on the state psi. Actually, it turns out that this subset is actually a subgroup of commuting Pauli operators. And the bigger is this subgroup, the more structured the state has. And in the best case scenario, this subgroup is exponentially big, is maximal side. And here we have what we call no magic states, which are also stabilizer states. And there is a one-to-one connection to stabilizer group and stabilizer states, because we can write the density matrix of stabilizer states as an isotropic sum of Pauli operators belonging to the group. OK, now what is magic? Magic is just somewhat the distance between a state and a set of stabilizer states that you can quantify in different ways. Here we're adopting this notion, which is just counting how many Pauli operators fails to stabilize the state. But in this talk, you can always imagine, just trust me, that this measure nu is just the T-count. The T-count is just the number of T-gates or non-Clifford gates used in a state preparation circuit of the state. Cool. So, OK, so we like to study these resources. From my perspective, the reason is the following. So both of them quantify somewhat the complexity of the state. If you have low entanglement, you can simulate classically the state or learn it efficiently. Equivalently, if you have low magic, then you can learn it and classically simulate the state. And in principle, these two resources really don't talk to each other. You can create states with arbitrary high amount of entanglement and low magic and vice versa. And our question is the following. Is there a setup in which these two resources do interact non-trivially? In other words, to put in more rigorous statement, and what is the difference between high magic entanglement and low magic entanglement? It turns out that the perfect playground to try to answer this question, at least in a fashion, is to take an operational approach. What does it mean? We want to study how magic enters in the complexity of entanglement manipulation tasks. Entanglement manipulation tasks are of various types. Here we, for example, analyze maybe the most famous one, which is Bell pair distillation. Imagine that these two far distant parties, Alice and Bob, have this entangled state A and B that they share. Say that they have k copies of them, and they don't know the state. The state is unknown to them. But their task is to use LOCC, so local operation and classical communication, local operation in their lab, and then they can communicate the measurement result and their intentions to each other to produce some EPR pair. This M plus is given, it is the number of EPR pair produced by per copy of the state psi. This task has been studied a lot in information theoretic sense, and the ultimate limitation of manipulating this entanglement and transforming it to EPR pair is the following. So the optimal rate in the information theoretic sense is given by the phenomenon entropy. That's why entanglement theory as this, the phenomenon entropy is the most important entanglement quantifier in entanglement theory. Okay, very similarly, we can imagine the converse task. This time, Alice and Bob share some EPR pair, and they have locally prepared in their lab, respectively, some copies of the state psi, which is very large and is unknown to them. And they want, again, to dilute the state non-locally across their lab. And then you can quantify the performance of a given protocol by looking at the rate. And the optimal information theoretic rate is again given by the phenomenon entropy. And this is a second reason why we love so much this entanglement quantifier for bipartite pure state entanglement theory. But it is also saying some cute fact about bipartite pure statist entanglement theory, is that it is a theory which is reversible. If Alice and Bob use a bunch of Bell pairs to produce some state, to dilute its state non-locally, then they can change their mind, and then they can actually distill all those EPR pair back, promise, of course, that they use the optimal information theoretic protocol. OK, so now let us take a step back and think, what are we doing? So we know computational constraints, which I will introduce in a minute, maybe in 30 seconds. These tasks are kind of trivial to accomplish. For example, is this remarkable example of the Hayashi-Matsumoto protocol that uses exponentially many copies of the state to produce EPR pair at the optimal information theoretic rate. So to make a meaningful statement, we want to introduce some computational constraints that comes in two layers. The first layer is that we want to use only polynomially many copies of the state to begin with, and we want to use LOCC that run in polynomial time. Remarkably, for stabilizer states, both tasks that I introduced before are efficient even in the agnostic scenario. You just need to use linearly many samples, and the LOCC run in polynomial time. So the precise question we would like to answer now is how magic introduces complexity in this framework that we can call entanglement learning framework. OK, I hope that now the question is a bit clearer. And now let's look at how we answered this question in our paper. OK, so it turned out that a useful way to answer this question is to divide the Hilbert space in two regions, or into classes, or two phases, whatever you want to call them, of states. One of those is called entanglement dominated, because it's characterized by the fact that the entanglement, the phenomenon entropy is strictly larger, is small omega, strictly larger than the magic in the state. On the other end, we have the magic-dominated states, which are those states for which the phenomenon entropy is somewhat upper bounded. If you scale the number of qubits up, always upper bounded by the magic in the given state. And we will see that these two classes have distinct computational properties. So let us look at the entanglement distillation task that I introduced before. You have this unknown state. You want to distill Bell pair from it. If you are entanglement dominated, we prove that there exists a protocol which is sample efficient, that works for unknown states, whose rate is asymptotically optimal. So it works at the rate of the phenomenon entropy. Whereas, conversely, in the magic-dominated scenario, we prove that there are classes of magic-dominated states such that the rate cannot be better than a vanishing fraction compared to the information theoretic distillation rate. So you see that if you scale up the number of qubits, then these two phases, classes, ensembles, whatever you want to call it, of states, then separate each other, and this separation takes place in the entanglement efficiency, sorry, in the computational efficiency of this entanglement distillation task, which is bell pair distillation. Very, very similarly, for the dilution task, it happens the same. If you are entanglement dominated, then you can actually achieve the information theoretic rate up to an error that goes to 0 if you scale up the number of qubits. And conversely, in the magic dominated case, you are screwed. You cannot achieve if you constrain your protocol to operate on polynomially many copies and to have polynomial time complexity, then the protocol cannot achieve the information theoretic rate. So let us summarize and look at the big picture together so we can have fun. And on the z-axis plays this and the entanglement landscape. So we see that this is a cartoon, of course. We see that the entanglement-dominated states have the entanglement landscape, which is very, very smooth, because we can manipulate entanglement agnostically and very efficiently. And therefore, the reversibility of the theory is preserved, of course, always when you scale up the number of qubits. Conversely, in the magic-dominated states, this cartoon says that the landscape is steep because there are probably classes of states for which you cannot operate at the optimal information theoretic rate. So one very small remark, this separation makes sense always if you scale up the number of qubits and these two phases of states slowly separate from each other. OK. So now let's look briefly at the methods we used. And I will try to give you, I will avoid technical details due to time constraints. But I will try to give you the idea about how we arrive to prove these results. So when you deal with, so this is about magic, right? And when you deal with magic, then it's always useful to look at the trivial case of stabilizer state, which are by definition those that have no magic. So stabilizer states, there is a bijection between stabilizer states and stabilizer group. And the stabilizer group is generated by n, which is number of qubits, algebraically independent Pauli operators. This is called the generating set. And there are multiple generating sets. But there is one that you can manipulate and partition in the following sense, into three subsets. The first subset is given by those Pauli operators that act trivially only on A, act non-trivially only on A, as B, the same, they act non-trivially only on B, and then you have SAB, which is just all the rest, that act non-trivially across the bipartition AB. And Fatal and Bravi just showed that the von Neumann entropy of stabilizer states is given by the cardinality of the latter set. This is not surprising if in your mind came the fact that any stabilizer state is locally Clifford equivalent to a bunch of bell pairs, and this result is just counting the number of bell pairs that live across the bipartition. Okay, the question is, can we borrow this simple concept and talk about now magic state, not just the trivial case of stabilizer states? So there are two facts that should be proven, but now I have no time, that a state with magic nu possess. The first one is the magic compression that also happens for free fermionic and free bosonic states. So every state with magic nu can be compiled in this way. So you have a Clifford in which you can see it, or you can imagine it generates entanglement, acting on a bunch of zeros and on a magic state on only nu qubits. So this guy generates magic, this guy generates entanglement. The second fact is that still, for magic state, we have a notion of stabilizer group anyway. The bigger is a stabilizer group. The closer is the state to be a no magic state. And the remarkable fact is that for any value of the magic nu, this stabilizer group is always efficiently learnable with linear number of samples. OK. So we can be dumb here. We have a notion of stabilizer group. And we can take the generating set and just define, in the same fashion as we did for stabilizer states, we can define the stabilizer entanglement, which is just a cardinality of SAB, which is the set of Pauli operators that act non-trivially on A and B simultaneously, divided by 2. This is a pointless definition, but 2 results can be proven that make this quantity meaningful. The first one is that this guy is not an entanglement monotone, of course, but is non-increasing under stabilizer LOCC, which are those LOCC in which instead of acting with local unitaries, A and B, you restrict these unitaries to B Clifford. And then the other theorem is that the stabilizer entanglement tightly bounds the von Neumann entropy from above and below. And the error that you make in this bound is just given by the magic of the state here. Now I claim, maybe it's a bit hard, but now I claim that you have all the tools to grasp the idea behind the separation of entanglement and magic phases. So okay, so you have the magic compression theorem on the left, so that any magic state can be actually compiled by a big Clifford that generates entanglement. And you have on the right the fact that a very simple quantity, which can be efficiently learned, a upper bounds from above and from below the von Neumann entropy. So if you remember the definition of entanglement dominated, in which a von Neumann entropy of the state is much larger than the magic, then it will be, if you scale up the number of qubits, you immediately understand that the von Neumann entropy actually happens to be the same, at least in the leading order, of the stabilizer entanglement. And the stabilizer entanglement being not increasing under stabilizer LOCC, then it turns out to be very efficiently manipulable in an agnostic sense. So see, this is the rationale behind the stabilizer entanglement. For magic-dominated phase instead, you can imagine that these states arise when the Clifford there is not so entangling. It does not generate entanglement which is stabilizer. So you have the worst case in which this C act identically on the bunch of 0 and on the magic state. So you have this case. And here, this state is generic, is whatever you want. So you can encode in this state the so-called pseudo-entangled families of states, which are 2 families of states that cannot be distinguished by efficient protocols, yet they display different amount of entanglement. The fact that they are not distinguishable by any efficient protocols tells you that, but they have different entanglement, tells you that the entanglement seen by efficient algorithm is not the full one. So efficient algorithm cannot perform in the information theoretic way. That's why we have this separation. I hope this is remotely clear. Now I want just to look at these results from another perspective. And that's going to be my final slide before the conclusions. So I told you that you could have imagined this magic thing to be just a T count. How many non-Clifford gates you use in the state preparation circuit. So you have here a Clifford circuit with a bunch of T gates that prepares the state. Then you have a very famous regime, which is the regime of classical simulability and efficient learnability of such states. If the number of T gates scale logarithmically with the number of qubits, then these states are efficiently simulable, efficiently learnable, they are very easy. This work highlights the fact that actually there is another regime which lies strictly beyond the classical simulability barrier or learnability barrier, in which the state is no longer simulable, is no longer learnable, but the entanglement can be learned efficiently. We can efficiently learn how to manipulate entanglement of such states, even if we believe that those states are not classically simulable. And then, OK, then you have the red regime, in which there is full randomness. You can encode pseudo-random states there. So we don't expect that those states, you can learn anything from those states. OK, that comes to my conclusion, my summary. So we asked in this work, we asked basically the question about if there is a non-trivial way to let interact these two resources, magic and entanglement. And the way is to look at the efficiency of entanglement tasks. And it turns out that it was useful to define these two families of states, entanglement-dominated and magic-dominated. For entanglement-dominated, entanglement tasks are efficient and agnostic. For magic-dominated, this is no longer true. There are provably classes of states for which you cannot do anything better. One remarkable thing I would say, the one that I like the most, is that, of course, entanglement learning is weaker notion of learning than full state tomography. But here, in this work, highlights the fact that this separation is actually there. So it's strictly weaker because there are states for which entanglement is efficiently learnable and the state is provably not. And with this, I would like to thank you for your attention, and questions are welcome.
Questions? I see some hands.
Thank you for the really nice talk. Have you thought about, or what can you say about magic state injection and state preparation, considering you have this trade-off between the amount of magic that you can inject in a state at, let's say, one step versus how many stabilizers you have in your group, because that relates to how many stabilizers you can fix and thus post-select, increasing the fidelity of, like, let's say, the magic state you're preparing.
I think that, I mean, you can look at this in this setup here. I mean, you can imagine that each T gate, it's just injected by, it's just injected by a magic state injection setup, and then you can actually play the same game there. I mean, there you will have a state of n plus t qubits, but the game is the same. Yeah.
Can you draw any conclusions, or do you?
I don't think you can gain some more out of it, at least by now, yeah.
Thank you for the talk. I'm interested in your constructions of the pseudo-entangled state. Where are you coming from, the log cubed of n and the log squared of n that you had up on the slides?
Yeah.
Where's that coming from?
Here. So it's important that the number, so the magic here is super logarithmic.
Yes.
Okay, say log
It
cube.
used to be, yeah.
Okay, and then here you can play the game, right? You can encode a random state on new qubits, which is super logarithmic, so it's going to be super poly, the complexity to learn them. And then, for example, subset phase states with this size of the subset, expo this size of the subset, and then the entanglement would be different, yet you cannot distinguish between the two.
Thank you.
Thanks for the nice talk. I was wondering how much you can say about mixed states. So like distilling entanglement for mixed states using stabilizer operations.
Yeah, I mean, that's a very good question. And I mean, you can say something, but I'm not totally satisfied. Because, yeah, you can play the game. I mean, you can define, I mean, there are stabilizer mixed states, which are not crucially convex combination of stabilizer states. They are just states stabilized by less than n poly operators, but they are mixed. So they are projectors. The projectors on stabilizer group. You can play the game. You can extract sample pair out of them. You can also perturb them in this way, but I didn't find so much meaning into that, I would say. I mean, we have it in the paper, but I always prefer to stick to pure states and talk about entanglement learning, complexity, and stuff like that. But thanks for the question.
Thank you.
Thank you for the talk. So it seems like the entanglement measure you chose was like number of bell pairs. Can you say anything about if like higher partite entanglement might change the results, or?
Yeah, so no, okay, no, that's a very, very good question. Indeed, for tripartite entanglement, the results that do not change much in the entanglement dominated phase, there you have GHZ, because the same game here, sorry, this thing, no, sorry. here, what is it? Yeah, the same game can be played by the number of GHZ state for stabilizer states is here. Sorry. Yeah, the same game, but the number of GHZ state across a tripartite, the three-party partition. And then the same game can be played for stabilizer states. Therefore, if you have enough entanglement, then you can still distill GHZ state using stabilizer operations. Yes. And also you have the separation for magic dominated states. Yeah.
Thank you.